Well, welcome back to volume 2 of the second of my Balzan lectures, and I've rather lazily resorted to slides here. So, but there are blackboards on either side. So if you have any questions, I can explain on either side. The this talk then is based on a paper that came out just at the end of last year in December, and although that's a single author paper, it was very much rolling up work that I'd done with other authors, so the first part is based on a series of papers I've written with Claude Lebrun, although the one that it most naturally relates to is this one from 2007. And this, I just about got to the statement of the basic result of this paper last time, but in order to sort of carry on from there, I'll need to sort of go over that again this time. And this was all about gravity in split signature and this, in the self-duality equation. So why split signature? First of all, self-duality only has real solutions in Euclidean and split signature, not in Lorentz. The ideas all have versions in Lorentz signature, but if you want a tight statement, you go just about the self-dual sector, then split signature is the best if you want to have all the degrees of freedom of the gravitational field, which is what we want to do for scattering theory. And it's a version of the Twistor correspondence based on holomorphic disks in Twistor space, as I started to explain last week, and I'll carry on explaining today. And then the second half, so as I say, I'll review this in the first part of the lecture, and then in the second part of the lecture, I will go on to adapt these ideas, thinking more about these holomorphic disks in Twistor space as some sort of theory. You know, what is the theory of these holomorphic disks in Twistor space? These are the things that are going to correspond to points in space-time. Can we do computations in full gravity using these holomorphic disks? And the answer is yes, and what we will hope to do is to get at the end to gravity tree-level scattering matrix based on the Karo-Sigma model, whose field equations give rise to these holomorphic disks in Twistor space. And along the way, I hope to uncover this kind of so-called LW1 plus infinity symmetry that Andy Strominger was so excited about a couple of years ago, and to show the Twistor origin for these symmetries. So that's the plan of this lecture. Okay, so well, I should begin. So just for those who are interested in gravity scattering, I just want to start off by explaining the state of the art as it was 10 years ago with gravity tree-level scattering formulae. And as I explained last week, in 4 dimensions, if you have a vector, a 4 vector, you can convert it into 2 component spinners with both a dotted and an undotted spinner index. And I hope people are comfortable with this. I don't want to. And okay, so then if it's a null vector, it turns out that the 2 by 2 matrix here is simple. It's the outer product of 2 vectors. And so I'll call these, if the momentum vector is called K, then these would be kappa and kappa with a dotted index. And the picture here is that we've got a scattering process in which we have, just very naively, a bunch of gravitons coming in, another bunch coming out, although there is a convention whereby you have them all going in, it doesn't really matter too much. And so they each have momentum K1, K2 up to Kn. And if you split the momentum into its constituent spinners, the scale of the constituent spinner actually encodes the polarization data. So it's meaningful data to actually separate out the spinners. Now, it's tiresome to have all of the indices flailing around everywhere. And so quite often when you want to write formulae, you write the contractions for the undotted spinners with angled brackets, the dotted spinners with square brackets, and maybe if you've got a vector and 2 spinners, you might do this bracket notation with angle and square brackets, just to get sort of more compact formulae. So when I first started in this subject, we were told not to compute Feynman diagrams. They're terrible things. Bryce DeWitt in the 60s would cover page after page after page to get the 4-point amplitude. But technology has progressed, and over the years, the 4-point amplitude was where you're at, or maybe 5-point was where you're at until the 80s. And then the KLT formula came in, and Berens, Gielen and Quiff came up with a formula which is still quite terrible when you look at it. Sum over permutations and sort of long, unmotivated terms. And then Andrew Hodges, just by staring at things and thinking about symmetries, came up with a beautiful formula 11 years ago in terms of the determinants of a matrix. So what did he do? You've got these n particles. They have these momentum invariants with angle brackets and square brackets. He wrote down this matrix Hij, whose entries are just the ratio of the square to the angle brackets. And he adjusted the sort of diagonal terms so that the row sums were all 0. And when you do that, it's actually automatically a degenerate matrix. And you can write down a reduced determinant. So there's a reduced determinant that has the full permutation invariance. And in fact, you have to strike out 3 rows and columns here. And you end up with this formula for the MHV amplitude where particles 1 and 2 have negative helicity and the remaining particles 3 up to n have positive helicity. So this was the formula, and it was really just arrived at by staring at other people's formulae and playing around with symmetries. There was not really a good reason, and if you looked at all of the Feynman diagrams, you just get chaos. I mean, you just get page after page of stuff, and so you ask the question why. Well, it turns out actually that Andrew's formula was not the first formula that had nice structure for the MHV amplitude. It was observed by Feng and He within a couple of months that one way that this formula might arise is by usage of the matrix tree theorem. So the matrix tree theorem says that if you have a sum of tree diagrams, you can actually, and if the propagators, if the edges have parameters that could be any number, but here the edges are given by that quantity between nodes I and nodes j, then the sum of tree diagrams could be expressed as a reduced determinant. And in fact, some 14 years earlier, there was a tree diagram formula rediscovered 12 years later for this gravity MHV tree amplitude. So again, you ask the question why. Why these expressions? These are a long way from what you'd expect from Feynman diagrams. Feynman diagrams have got poles which look like 1 over the momentum squared of sums of particles. It's very unclear. But this is something that I hope to answer in this talk. Yes?
So for this matrix H, the second line, when I equal to J.
Yes.
It's not balanced with respect to helicity of particle K.
I know, I've fudged this a bit. You've got to put in some reference spinners and stuff. But you can make it I didn't want to have the full complexity there. You choose 1 and 2 and you put them in. I just didn't want to write out the...
Should not have helicity with respect to particle K. Do we agree with it?
That's right, yes. So you had to put in a couple of reference spinners, and you do it using 1 and 2. Yeah. Okay, so you're seeing this. I took some shortcuts in my slides here to make them simpler. Yeah. Okay, so anyway, this is a mystery that I hope to explain. And I also, in the last week, I gave some of the motivation for twistor theory, but I just want to sort of talk about another aspect which I didn't have time to present, which was the idea that you could reconstruct spacetimes from infinity. This is something that Ted Newman tried to do in the 1970s. He said that if you have a point in a Lorentzian spacetime, you can follow its light cone out to infinity, and that gives you a cut of null infinity. And he wrote down what he called the good cut equation, which was hopefully going to correspond to points in the interior spacetime, and they failed to do so. And instead, you end up with what's known as H space. It's a complex space-time, and it has self-dual Weyl curvature. It's Ricci flat, but it has self-dual Weyl curvature. And you think of it as projecting out, in some sense, the self-dual part of the gravitational data at Scry, and producing the space-time that has that data. Roger Penrose reinterpreted this using an asymptotic Twistor space in terms of the nonlinear graviton. And the nonlinear graviton took the idea that you could start off with a Twistor space. I talked about this last week. You could take a Twistor space, CP3. The lines in the Twistor space correspond to points in space-time. The Riemann spheres in Twistor space of degree 1 correspond to points in space-time. And if you deform that, then you get a deformed space-time, which is self-dual. And in some sense, this construction embodies the complete integrability of the self-dual sector of gravity. And it's now understood that the self-dual sector of gravity is an integrable system, and as a consequence of this construction, essentially. So you can write down data for general solutions. You can find exact solutions. People like Nigel Hitchin and Michael Atiyah and so on sort of did wonderful work using the Twistor theory to construct solutions. And it was possible because of the integrability of the self-dual sector, and that was embodied in the Twistor theory. And so then the construction, as I was explaining last week, rests on finding holomorphic degree 1 Riemann spheres in the deformed Twistor space. And this chiral sigma model is going to embody the theory of those spheres. And by just thinking about that model and playing with this a bit, we're going to see that we can get the full gravity S matrix by expanding around the self-dual sector. So that's going to be the main idea. But it still has some of the symmetries of the original sort of nonlinear graviton, and that's where these LW1 plus infinity symmetries would be coming from. Okay, so these are the introductory slides. Any questions? Okay, so I wanted to sort of state again the result that I ended my talk last week with. And so what I want, so the aim here then is to talk about sort of the global solutions of the self-duality equations in split signature. And so just to give you a picture as to what they should look like, by global, you take the conformal compactification of spacetime. So if you have split signature spacetime, that's R4. You add on this light cone at infinity, so there's a kind of a picture that any relativist will have seen, whereby you add on a light cone at infinity. In Lorentz signature, the light cone actually has two components. It has one in the past, Scry minus, one in the future, Scry plus. So you think of this as a dotted line down the middle. It's the center of some rotational symmetry. And when you form the compactified spacetime, you have some identification between Scry plus and Scry minus, and the spacetime becomes conformally flat, and it's a homogeneous space for the group SO33, maybe divided by Z4. And so if you actually look at the topology of this space, what you discover is that this is the projective quadric inside RP5, which is acted on by the SO33, and that has topology S2 cross S2 divided by Z2. Now, this Z2 is sort of a little bit problematic. It's the one that identifies Scry plus with Scry minus. So you can imagine if you have any kind of non-trivialities to the scattering, then it's not going to work to identify them. And so you could just take the double cover, and in which case, if you take the double cover, then instead of getting S2 cross S2 divided by Z2, you get S2 cross S2. Another feature to notice also is that if you're working in Lorentzian signature, there is no longer any such thing as past and future. So this picture is at best misleading. there are 2 time dimensions and 2 spatial dimensions, and you could do a rotation in the time dimension to take yourself into the past of any one of them. So you had to think of the scry as being, it doesn't have 2 disconnected components in split signature. It has this topology S1 cross S1 cross R. And so if it's S2 cross S2, we can think of the metric as being the round sphere metric on one factor minus the round sphere metric on the other factor times some conformal factor. And here we can just think of these as being unit spheres inside R3. And the Z2 is going to be the double antipodal map on these 2 spheres. So in that case, then the scry, this hypersurface at infinity, is going to be what you get by setting the x3 components equal to the y3 components on these 2 spheres. And so it's difficult to draw in 4 dimensions, but you can see that x3 equals constant is a circle in the first sphere, and y3 equals constant is a circle in the second sphere, so you get the S1 cross S1. And then the value of x3 going from -1 to +1 is going to be the R factor. So that's makes the whole compactified space look just like a homogeneous space, 2 spheres. And it's sort of relatively easy to see it's going to be acted on by SO33. So that's the flat model. And then we're going to be thinking about deformations of the flat model. And so we want to introduce curvature. So in 4 dimensions, it's a general statement that, the nice way to think about how the curvature decomposes in 4 dimensions is to think about the curvature as sitting inside 2 forms tensor 2 forms. And but the 2 forms in 4 dimensions break up into self-dual and anti-self-dual under the Hodge duality operation. So these are star f equals plus f, and these are star f equals minus f. And if you do that, then the Riemann curvature as a matrix over 2 forms, a symmetric matrix over 2 forms, has the Ricci tensor in the off-diagonal components and the Wahl curvature in the diagonal components. And this lecture will be focused on the case where you have, or at least the first half of the lecture will focus on the case where the anti-self-dual Wahl tensor is vanishing, but we also have the Ricci tensor vanishing, and that will have the benefit that these anti-self-dual 2 forms are flat. So we're going to have constant anti-self-dual 2 forms, and that means we'll have constant lambda alpha spinors as well. So the 2 forms, omega 2 plus, they're really corresponding to F alpha beta with a pair of spinor indices which are symmetric. Okay. So why do I need to look at that? Well, it's because I'm going to be focusing on the Twistor space. So the Twistor space is the space of these totally null 2 surfaces, which I talked about in more detail last week with a slightly different framework. So they come in 2 types. They come in a self-dual type and an anti-self-dual type. And so the anti-self-dual ones can be obtained in this picture when x is a rotation of y. So you have an S2 sitting inside this space, S2 cross S2, given by the submanifold where x is given. You fix a constant rotation A, and x is going to be a rotation of y. And so it's easy to see that that minus that then vanishes, and this will then give you a totally null 2 plane. And that's what we meant by if it's anti-self-dual, that's actually what we mean. Well, last week I used the term beta plane, alpha plane for that, but here in fact it's more normal to use the term beta plane. And so when the anti-self-dual Wahl tensor vanishes, these will survive as surfaces in the curved space-time. So we will still have a space of these twistors in this case. And we can still study the properties of the space-time via the space of twistors. These twistor spaces are completely visible, they're real, and they form RP3. The complex twistors, so you can imagine that there are some twistors in the complex corresponding to complex anti-self-dual two surfaces or planes. They will generically intersect this space in a unique point. So we will still be able to think about them because they do intersect this space, but just in a point. I'm not going to talk too much about them because that they form part of the proof of the theorem that I'm not going to describe.
By the way, in the usual signature,
yeah,
for the anti-self-dual or self-dual of the same condition, what are the beta planes? What are the total in space-time?
Right. So here I've given them in terms of this representation. So last week I gave them in terms of this representation. So these are the beta planes, the anti-self-dual beta planes, and the so those are beta planes, and then the alpha planes are the just the conjugates. So you have undotted interchanged with dotted. And here, of course, you reverse the orientation if you have something with negative determinant. So the alpha planes are the A's with negative determinant there.
And in the four-dimensional space-time, so this becomes complex.
Right. So these equations will be meaningful in the complex as well, for complex mu, lambda, and x. And there's a statement that in the flat model, every complex alpha plane or beta plane intersects the real slice in a point, or in 2 points here, because if you've taken the double cover.
But if I take a nonlinear graviton,
yeah,
these are what in complex space-time?
In complex space-time, these are two surfaces. They're totally null two surfaces. So yeah.
Two complex dimensions.
Two complex dimensional, yeah. So there are integrability conditions, and the integrability conditions are precisely the statement that the anti-self-dual Weyl tensor should vanish, so that the Weyl tensor should be self-dual. And that's the only condition. So we don't need to use the Ricci flat condition at this stage. Okay, so these are very nice, even in the curve case. In particular, they're totally geodesic and they're projectively flat. So the curvature vanishes on them, and they're actually projectively flat. So so in fact, if you start to look at the structure of these surfaces, and if you make some global conditions that they extend as far as they can, that the light rays are in some sense can be extended to infinite values of their affine parameter, then you discover that, well, if they're compact, they have to be necessarily S2 or RP2, so to be projectively flat. And you discover that null geodesics then inside these S2s or RP2s have to be a whole line, or it's a whole line in the plane, or a great circle on the sphere. So, okay. So as a nice global condition then for sort of null geodesic completeness, it's natural to introduce this definition that Gieleman had of Zoll-Frey, which are essentially the statement that all null geodesics are embedded circles inside the space-time. And so these are the spaces that Claude and I set out to classify, and our theorem then gives you a complete classification. So of course, if it's flat, you can have this S2 cross S2 divided by Z2, but if it's non-flat, if it's not conformally flat, then the only case that you can have is that the manifold is S2 cross S2, but there are many, many of them. So there, you might have assumed that there was some sort of rigidity, but we prove that we've got a lot of these conformal structures. So we're just here looking at the self-dual Weyl curvature condition. We haven't yet focused on the Ricci flat condition. And if you make this global assumption, then the topology is S2 cross S2, and the self-dual conformal structures on S2 cross S2 are in one-to-one correspondence with the deformations of the standard embedding of the real slice of RP3 inside CP3. So that looks like a bit of a cryptic statement. So just to make it a bit clearer, you can imagine that inside. You can imagine that what we're doing then is inside just the ordinary flat CP3, you can take the RP3, the standard one, and then you can take some tubular neighbourhood, which I'll just refer to as I times R3. So here we have the real slice, the RP3, and then in the transverse direction, we have I times R3 going off into the complex part of CP3. And here we're imagining that we're writing the twistor Z as U plus IV. So U is the horizontal axis and V is the vertical imaginary axis. And then what I'm saying here is that the deformed real twistor space, PTR, you take the real RP3 and you just push it up. It's the graph of some function. So you can express it as a graph V equals some function of U for some free function from RP3 to R3. And this is a complete gauge fixing for the thing, and these you expect there to be three real functions of three variables worth of data for these solutions, and this gives you a perfect parametrization in the sense that this is a one-to-one correspondence, at least for small data. Okay, so this somehow gives you the a perfect representation of the space of solutions here.
But F needs to be C infinity.
I didn't. I think we stated the result for C infinity. We stated and proved it for C infinity. One could, if one wanted to do some work, deal with lower regularity. And I don't know how low you can go, but because it's complex analysis, you can go very low.
Not as low as Nash, but anyway.
Right. Almost certainly not as low as Nash, no. But actually, you might be able to. I mean, there are Newland and Nuremberg proofs that are now kind of they're not even C1. I mean, they're not. The assumptions are not enough to actually make the nine-house tensor vanish strongly, I think. Okay, so that's what it buys you. So it is, in some sense, a perfect classification. So there's two directions. We go from the self-dual spacetime to this deformed embedding. And we use the fact that all of CP3 should be accessible because every complex twistor should intersect S2 cross S2 in a point. So we can somehow construct this compact CP3. And that's rigid, it has no deformations when it's compact. But then the location of the real slice inside it has shifted.
By the way, when you say CP3 is rigid, what structure of CP3?
Sorry, okay, the complex structure of CP3 is rigid. Okay. Yeah, and but that's all we need for the nonlinear graviton construction is the complex structure, so yeah. Okay, so that's the statement that Claude and I had from 15 years ago. And then the thing that's maybe more interesting is how did we reconstruct the space-time?
Duty-free, these things, zone phi.
Well, that was a joke on the. So the first paper that Claude and I wrote on this kind of general class of twistor correspondences that uses holomorphic disks was one on so-called Zoll manifolds. So Zoll manifolds are. So Otto Zoll set up this problem of.
Mr. Zoll.
Yeah, it was Otto Zoll. And so Otto Zoll sets up a problem of classifying all the metrics on the sphere, all of whose geodesics were closed embedded circles. And then the joke is actually a joke of Victor Gieleman, who started talking about spacetimes in 2+1, all of whose null geodesics were closed. So here was the person who made the kind of bad joke that these things were Zoll free. Yeah, that there was.
Which means duty-free.
Yes, that's right.
Go around without paying tax.
That's right. That's I think was Victor Gieleman's joke. Yeah. Okay. Yeah. So that was a paper we did first, but then we did the four-dimensional paper after that. And okay. So then the the main part of the proof of this that I want to talk about in a little bit more detail, though, was how, going from here to here, one could just do some manipulations to reconstruct the CP3 and the embedding inside, which were non-trivial, but they, and you needed a very low regularity version of the Nylander-Nirenberg theorem. But going back from here to here, we need holomorphic disks. And the idea then is that at each point in space-time is going to correspond to a holomorphic disk inside the complex projective 3 space, here in the cartoon, just given by this blue curve here, such that its boundary lies on this deformed real slice. And so the whole point of this is that this is an elliptic problem, and you expect it to have a finite dimensional family of solutions. And you can count the number of solutions that you expect if you know its topological degree. So dx has topological degree 1 in the sense that if you were to just double it, reflect it, you would get a line, you would get a sphere that.
Holomorphic disk. This is
Yes.
topologically a disk with
Yes.
a complex structure which satisfies some boundary condition on the boundary of the disk.
Yes. Okay. I'll need to say this later anyway. So if the disk is a map from the, the disk, of course, you often think of it as the interior mod z smaller than 1 inside the complex plane, but yeah, and so you have the holomorphic disk is a subset of the complex plane, which is at least biholomorphic to the disk. I mean, it could just be the upper half plane. And, well, it will later be the upper half plane. I mean, here we don't need to make that choice. And then we have a map. dx goes into the CP3, which is holomorphic map. The coordinates are holomorphic functions of the parameter on the plane. But then we also have the boundary condition that this real axis, or the boundary of the disk, has to lie inside this PTR, this real codimension 3 hypersurface inside the.
F of u is not analytic, it's just C1, C2. This
you can probably get away with C1, yes, yeah.
That's not a problem to have the boundary just C1 and to have the interior with all.
You'd have to ask Gromov. I think we were lazy and probably just did it in the smooth category, but I know that the regularity conditions.
Smooth is okay.
Smooth is easy, yeah. Okay, so in the reconstruction problem, then, dx. There's a relative cohomology analog of degree, so d and its boundary inside the twistor space were relative to this PTR, this real slice. It has topological degree 1. And you can prove that that the moduli space is four-dimensional. You just look at the linearized equations, and these are just ordinary functions on the upper half plane that are real on the boundary, and they're twisted in such a way you get 4 solutions. So you get a real four-dimensional moduli space that's compact, and that does come out of sort of the kind of Gromov type theory. And I'm glad it's not here to pick me up on all sorts of details. And and it doesn't take long to prove that it must have the standard topology S2 cross S2. And what takes maybe a little bit longer, but it's sort of somehow standard technology in the Twistor law, is to show that this manifold actually has a conformal structure. And the conformal structure is constructed by thinking of each of these disks in the real Twistor space has a boundary that looks like a circle, but just locally it looks like a line. And there's a codimension 1 condition that 2 of these lines will intersect. So if you have a boundary of one disk, x prime, another one which is x, then the condition they exist is a codimension 1 condition. And just infinitesimally, you can check that in the tangent space, this actually is a quadratic condition. And that follows from some version of Liouville's theorem that it's quadratic. So points here will correspond to 2 surfaces in the spacetime, which will end up being our beta surfaces. So points in the Twistor space, all the lines through a point here, there'll be 1 through every direction, and you can see that that's going to give a 2 surface in the spacetime, which is a beta surface, and the integrability of those beta surfaces was the vanishing of the anti-self-dual Weyl tensor.
The incidence relations between the 2 disks is that they touch, they intersect?
If they intersect, so 2 lines just intersecting transversely, if they touch, they will be the same. Yeah, these are the boundaries of the disk inside the real Twistor space.
And they intersect.
And if they intersect, then the 2 points are null connected. That's the main statement. Okay, so you can reconstruct the conformal structure on this 4-dimensional moduli space. So this is in some sense the proof that the data was free, because we can do this whenever we have that.
And the counting, because I understood that the counting of 4 for the Newman's cut equation is just the counting of the 3 wire lengths for the, you have an equation and you just count the linearized homogeneous solutions. It's like the good cut equation, your equation.
Yes, these are all equivalent to d-bar equations, and so in some sense you're actually counting the number of holomorphic functions on the disk that correspond to tangent vectors that are real on the real slice, that are tangent to the PTR on the real slice. And so when you count holomorphic functions on the plane, you have a version of Liouville's theorem. If it's on the half plane and they're real on the boundary, then you can reflect it in the other half plane, and then it's on the whole plane, and you can use a version of Liouville's theorem. Okay. And that counting is what you use. You could, if you were feeling fancy, sort of relate it to some index theorem or something. But yeah. Okay. So that's how the spacetime gets reconstructed. It gets reconstructed by looking at these holomorphic disks. So they play a big role, and they'll play a big role in what follows. But this theorem from 15 years ago was a statement about spacetimes that had anti-self-dual Weyl tensor. So what if you want it to be Ricci flat too? So we made no assumptions about this deformation of the real slice here, but presumably inside this, you could make some special choices of the f that would mean that you're actually in the Ricci flat case. And so that's what I want to turn to next. So again, we can adapt this Penrose's nonlinear graviton from 1976 to this split signature context. And so here we use the parameterization of Twistor space that I introduced last week with lambda and a mu, and with these instance relations with the spacetime, and these are homogeneous coordinates for the complex projective 3 space, and you can introduce a Poisson structure just in the mu variables. So it's just using the skew Levi-Civita symbol and the dotted spinners to define a Poisson structure. And you can also introduce a degenerate contact form, just a one form here. I mean, another way of saying that is that you have a projection from the CP3 minus a line, minus lambda alpha equals 0, that projects onto the Riemann sphere just by taking lambda mu goes to lambda, thought of as homogeneous coordinates on the Riemann sphere. And but framed in this way, you can show that you have a vacuum metric inside, a Ricci flat metric inside the conformal class when these are both real on the real slice. So this really is just following what Roger was doing 50 years ago or something.
The equation, the incidence relation you wrote in alpha dot is only valid in the flat.
That's only valid in the flat case, yeah. Okay. So there were... simple formula here. No.
But the coordinates are still the one of the flat thing. You use the lambda mu of the...
Yes, you can do that, yeah. And we will carry on doing that. But because we know that the global twistor space is CP3, we can still use the mu's. But we don't necessarily know that they're going to be real.
Even by this formula all over.
Yes, yeah. Okay. So this defines a complex Poisson structure and a complex one form over the whole of twistor space. But the condition is that when you restrict it to this deformed real slice, it must be real. Okay. So this is a little bit of a implicit way of saying it, and one can get very explicit. So if you write the homogeneous coordinates in terms of their real and imaginary parts, you can write down a generating function that satisfies that condition. And in fact, one's motivated here by the integral formulae I wrote down last week. The integral formulae started off with, for the self-dual Weil tensor, I had a homogeneity degree 2 twistor function. So here I might think that this could be used in a non-linear case too. So this is meant to be a homogeneous function just on the real twistor space, homogeneity degree 2. And then the real slice, I'll define it non-projectively, and then projectivizing we'll get the projective real slice. And we can just say that the imaginary part then has to be given by the Poisson bracket of H with the real part. So that's the definition. And if you write it out explicitly, the lambda part has to be real. So we're, in some sense, we're using the fact that there are covariantly constant undotted spinors. They are going to be global on the space-time, and they can form two of the coordinates on the twistor space. But the mu part, the imaginary part of the mu part, is given by this sort of generating function expression in terms of the real part of the mu part, which is the u beta dot. So the claim then is that all, so to speak, small enough Einstein vacuum twistor data are given by these homogeneity degree 2 twistor functions.
These are now not homogeneous but affine coordinates. So the function h,
yes,
I can take any function of the u dot, or they have homogeneity conditions.
Yes. So h is a function. Well, so a priori you think of it as a function of 3 variables, but you lift it to 4 variables, the homogeneous coordinates with this homogeneity condition.
And as I have only 2 u dots, so I take any function of u 0 dot, u 1 dot.
Oh no! This is a function of all 4 twistor variables.
Ah, okay.
So of the u alpha and the u alpha dots with that homogeneity condition, which reduces it to 3 variables.
And global regularity.
Yeah, and again, it's going to be smooth and globally defined on the real projective 3 space.
And you can write zillions of them.
That's right. So 3 functions of 3 variables. This is the complete expected functional degrees of freedom. And so the claim is that if you define your real slice in this way, using this homogeneity degree 2 generating function, then going through the procedure that Claude and I developed, you'll get a split signature vacuum metric self-dual, and they'll be Zollfrei as conformal metrics, but they will have a null infinity, which is modelled by what we had in the flat case, by the x3 equals y3 in the flat case, conformally flat case. So we think of them as being sort of, I mean, you really should think of it as a doubled up space-time. So it's got sort of two copies of space-time with a kind of a scry down the middle. So there's a kind of a scry with one, two copies anyway. You may only be interested in one of them, but there are two of them there. Okay, so this is the output of the theorem with Claude for the Ricci flat case. So that was the first part of this paper that I wrote, and this is the first theorem that I was meant to get to in my talk last week. Okay, so then, okay, any questions then? So there's from here we build on this.
What about the product of arbitrary Riemann surfaces? If we take just a product of two Riemann surfaces, are there conformally self-dual structures on the product?
Not in split signature. I mean, there may be some results in Euclidean.
You can make it split signature, right?
Oh no, but not self-dual. Sorry. So we excluded all topologies except for S2 cross S2. Yeah. Okay. So at this point, we can talk about, well, Jens Hopp's not here, but we can talk about W infinity and LW infinity and so on. So we can talk about how this is realizing the LW 1 plus infinity. So the thing that Jens Hopp showed has to be, I was about to say 40 years ago. Well, anyway, okay. So he showed that these higher spin symmetry algebras that Samologikov discovered in the 80s are Poisson diffeomorphisms of the plane. And just to flesh out what he said, I mean, I'll write this out in terms of the sort of things we've been talking about. So the plane in question is going to be the mu plane in Twistor space. And so the Poisson structure is going to be the one that we were just talking about, d by d mu, wedge d by d mu, roughly speaking. And now, to take the loop algebra, you need to have two extra variables. You need to have an extra variable. You've got maps from a loop into this space, and the loop here is going to be the projective line with homogeneous coordinates lambda alpha. So lambda 1 over lambda 0 would be some coordinates on the line, and
everything is real here.
Everything is real. Yeah, and so in order to actually flesh out Jens's theorem, you need to sort of choose some polynomial basis of the space of Hamiltonians, and for some reason you have this slightly weird indexing of the space of Hamiltonians. The mu's are in the numerator, the lambda, so it's polynomial Hamiltonians, and then because these were homogeneous coordinates on the Twistor space, you put enough lambdas in the denominator to make it balance. And this gives a very special version of this LW1 plus infinity algebra. And these are the commutation relations if you use those polynomials. So this is modulo some shifting, the algebra that Andy Strominger wrote down, which he discovered from his celestial OPEs 21.
And this symplectic two-plane, we have a two-plane,
yes,
which is symplectic. Mm-hmm. It is. The topology is
well. So it's really this. It's really this. Well, it's really sort of RP3 minus the line. So here we're looking at this structure that these are precisely the Twistor coordinates, and it's precisely where you see the structure. So it's RP3 minus the line in this case. Okay, so that's what the algebra is, and so in our language then, in terms of the result I just was talking about, you can think of the Hamiltonians that generate this algebra as being the H's that I was just talking about before. Now you can think about these Hamiltonians, you know, so just infinitesimal h's will do. So, so first of all, you could think about this Hamiltonian in two ways. If this is a real Hamiltonian, then it'll give you just a diffeomorphism of this real slice, this projective, real projective Twistor space inside the complex one, that preserves these Poisson bracket structures and the and this projection onto the lambda circle, roughly speaking. But we also thought about this h as being something that pushed you away from the real slice as a generating function. So one way is it's a structure preserving diffeomorphism, but if you multiply by I, it's telling you how to shift RP3 and deforming it to become this, to stick out in the complex. So the way that you should think about the self-dual gravity phase space maybe is as a complex version of this LW1 plus infinity, but here you divide out by the real ones to get you know, because these are just coordinate freedom, and the way in which we represented the shifted projected real Twistor space as a graph was a gauge fixing of that quotient. So okay, so then the claim is then that this Poisson bracket underpins Schrödinger's LW1 plus infinity structure. Okay, so how are we going to see this in the context of amplitudes? Sorry, any questions there? Okay, so Schrödinger had to do a lot of work to get there from Scry. He had to do a light ray transform, had to do a Mellin transform, and then he had to spot those coefficients were exactly the same as I showed you. So for him it was actually quite a mysterious thing, and here it comes straight out of the Twistor theory, complete with combinatorial coefficients.
Despite of the existence of a symplectic structure on Scry, the usual Scry, that was not...
Well, it's not. Scry itself doesn't have a symplectic... I mean, the Newman equation has a Wronskian, and you can identify this Poisson bracket with the Wronskian of the Newman equation. So that is a point of contact you can make. Okay, so what do I want to do now? So what I want to do now is I want to take these holomorphic disks more seriously. I mean, the original Penrose aspiration was to say that, you know, how you, well, I mean, his aspirations were quantum. He wanted to say, how can you do quantum gravity when your space-time events are God-given from the beginning? You know, you have to quantize the points. But here, all I want to do is think about it as classical equations. How are we going to think about perturbing around the self-dual sector? So we've just had a nice discussion of the self-dual sector. How can we perturb around it? Well, you can say, I'm going to put in some impurity. I'm going to sort of, so what happens if I've got k anti-self-dual gravitons in the mix? I want them to feed into this disk. I want them to sort of be sources. And so what I want to do is I want to say that if I'm going to have k anti-self-dual gravitons, I'm going to insert them at points so our disk is going to be the upper half plane now, just so that I can express the boundary as the real sigmas. And I'm going to feed in k gravitons at k points on the boundary of this Twistor, the boundary of this disk. And so what I'm going to do is I'm going to, first of all, insert a wave function at each of these k points, zi. So that's how I'm going to think about this. So this now is a disk where you have k perturbations by k gravitons. It's got to go through these k points zi, so it can receive it can receive a source contribution from the anti-self-dual gravitons.
You said wave functions. The zi are functions of something? Or?
Well, I'll put the wave functions in a moment. So at the moment I'm just setting up the disk so it can receive something. But this disk, writing it like this, means that, in fact, so this M is going to be real on the boundary and holomorphic over the interior. And so what you expect is that even in the curve case, when we've deformed this T, so this T is not the linear flat RP3, but it's going to be some deformed T, there will be a unique M with that boundary value. So I can pose the Zi's and the sigma i's, and then there'll be a unique M which gives you a holomorphic disk inside the deformed twistor space whose boundary is inside the real slice. So that's a claim that you just expect that to be the case. And I'm going to study the action for this holomorphic disk. So how do we write down the action? Well, first of all, for this to be in the real slice, the lambda part here from this part is already going to be real if the zi's are real and the sigma i's are real. So the lambda part is already real. So this M part is only sort of correcting for the fact that the mu part has been deformed. So that's the M alpha dot. And so you can write down an action. This M has to be holomorphic everywhere. And then you can add a boundary term to the action to require that this, on the boundary of the disk, that this M actually has the right values here to be inside TR. And so what you see is, in fact, just the H will do it. And the reason is that the kinetic term for this action is the Poisson bracket. So this, you just have the H as an integral around the boundary, and that will guarantee on shell that this disk has the right boundary conditions. So this is somehow the theory that we need to describe the disks in the presence of K anti-self-dual gravitons. And so we're going to have this H here, which is meant to describe the fully nonlinear self-dual part of the gravitational data. But then we're going to have K wave functions for the anti-self-dual perturbations. And again, when I wrote down the integral formulae last week, they happen to have weight, homogeneity weight -6 on the real twistor space. And we can take them to be momentum eigenstates even. We have this delta function form for the momentum eigenstates that I talked about last week. Okay, and later I'm going to expand the H in momentum eigenstates too, so just to get a completely perturbative formula. But as it stands, I'm going to write down the formula where the anti-self-dual parts are perturbative, but the H is fully nonlinear. And so this is the formula. So we take our on-shell action for the holomorphic disks, which is what I had on the previous slide. It's just this, so the previous slide, this is the on. So you evaluate this on the on-shell solution. And then we had these points Zi, which the disk had to go through. And at those points, we insert the anti-self-dual gravity wave function, H tilde I.
So do you need the explicit, so M satisfies d bar M equals 0 inside the disk, and no?
And the boundary condition that the...
And you need the solution of M, so it's a Dirichlet, I mean...
Yes, it's a Dirichlet boundary value problem. So you're specifying the imaginary part on the boundary.
To compute this and H and everything, do you need to solve this thing?
Yes.
And it's not, you cannot write down the solution immediately, or you say there is a Green's function boundary to bulk and M is equal to this?
You could start writing down Green's functions, but my strategy actually on the next slide is going to be to do perturbation theory. And
it's a linear problem or not?
Well, it's sort of linear, but when you write down the boundary value problem, it's quite a simple problem. So you can do the perturbation theory very explicitly.
Okay, but you cannot write the exact solution non-linear like this?
No, no.
It's not a linear problem?
No, no. Well, you make me think that maybe there's something one can do, but that's not the way I'm going to do it.
Does the integral converge?
Yes, but sorry, I'm just trying to think. I mean, this is an on-shell. Okay, we're going to boil it down to something that we know. So it converges in that sense. I think the short answer is yes. I mean, these integrals over the z's are non-compact, and they get treated in a yeah. But it is what actually will. I'll say it on the next slide. So you'll see that eventually it becomes sort of very well defined. But one can worry about intermediate stages. So the only thing that's mysterious in this, then, I put these sigma i's and zi there precisely so I could sort of insert these wave functions. The thing that might be mysterious here is this determinant, and it is plucked out of the air in order to give the right answer. I freely confess that. So this reduced determinant here is a tilde determinant. It's not the one we first thought of, and it's just constructed out of the Twistor coordinates of the z's, the lambda coordinates divided by the sigmas. So this is just some factor that we had to put in, and it's a reduced determinant of the same form we've seen before.
The rank of this matrix is what? Reduced means what?
Yes. So the rank of this matrix is k minus 1. So this is a k by k matrix, but it has rank k minus 1, and you had to reduce by 1. Yeah. But the theory of reduced determinants is nice. They're permutation invariant and everything. Okay, so you know, what are the key ideas in the proof here are to reduce this to a known formula. And the known formula in question was one that was due to Freddie Casazzo and David Skinner from 10 years ago, or just over 10 years ago. It came out soon after Hodge's formula. Once they saw Hodge's formula, they could see kind of how it might extend to arbitrary MHV degree. And
because here, the logic of what you are doing here, because you did not prove that the amplitude of k anti-central gravitational is given by this, you said this is natural to write down this, and then it agrees with the Hodges-Casazzo formula,
yeah.
No? Just to understand.
That's right. So there's an alternative proof at k equals 2 for the MHV. But for k greater than 2, the proof is to reduce to the Casazzo-Skinner formula. And so to do that, then we expand it all perturbatively. So this h that was a nonlinear thing, I can express it as a linear combination of momentum eigenstates, hk plus 1 to hn, and then we just take these to first order. When you do that, there's a standard routine for this. I mean, you know, if you're a quantum field theorist, you would write down a path integral. Because you're doing a non-shell action, you take the tree approximation, and eventually the connected trees are taken from the log of the path integral, and so on. And so it's given by, in some sense, the classical action for the disks evaluated on the solution is then given perturbatively as a tree-level correlator, connected trees on these vertex operators. And just to that order perturbation theory, we're getting this combination k plus 1 up to hk plus 1 to hn. And these are just the part of the action that came from each of these contributions. So the vertex operator is just that. And so the tree diagrams, they're any old tree. You know, you just have 15 legs coming out of here, and then another few from here, and so on and so on. The propagators correspond to the edges, and they're given by Wick contractions between two of the vertex operators. And they're given by taking the derivative. So they're given by this plus and bracket on the two h's, divided by the kind of standard Cauchy kernel on the Riemann sphere. And when you plug in these wave functions, the derivative respect to mu will pull down the momentum spinner. So you get these square brackets ij's divided by sigma I minus sigma j. And this is now looking like this, this Hodge matrix that we had on the first slide for the gravity tree amplitude. So the propagators for this action here are the entries of the Hodge matrix we had in the first slide for the MHV. But instead of having the angle brackets in the denominator, you've got sigma I minus sigma j.
You said you have K anti-self-dual graviton on top of a self-dual background.
Yes.
Here you have n minus K things.
So these are n minus K self-dual gravitons.
These are the self-dual because the n is the total number.
N is the total number. So in the first slide you see I had
self-dual.
Yeah.
They are where?
The anti-self-dual are in the rest of the formula here. So I'm just talking about expanding out this on-shell action. So you were asking, how do you do this? And I was saying, well, I'm going to do this perturbatively because I was trying to make contact with these old tree diagram formulae. So that was the point of it. And then when you do that, the you get tree diagrams with these as propagators. And then using the matrix tree theorem, we get this det prime of H now, which has the square bracket numerators. And so putting that in, you get the perturbative amplitude now has a det prime H, the det prime H tilde. They both look like they're now on an equal footing, but they're not quite because the H's are just inserted at the sigmas that these ones are, well, I mean, you get still in, these are just the Twistor integral, the Twistor wave functions. These ones here, though, are integrated over the insertion point, the Z. So it's an asymmetric formula still. And just to make one or two comments about this formula, this isn't quite the way that Casazzo and Skinner found it. They actually found a slightly more clever formula that had n equals 8 supersymmetry. But you can integrate out these Z's here when you have momentum eigenstates, and the formula completely localizes into residues. And at that point, you can see that this formula is a sum of residues on the Riemann sphere, on n copies of the Riemann sphere. So that's the sense in which this gives rise to something that's well defined. So yeah. Okay. So this
one is power n or n minus k.
That's power n. So there's k integrals over RP3, which are the insertion points for the anti-self-dual wave functions, but there's no analogous integral for the h. The z is already given. Okay, so that's the proof in that case. But I then said that sorry, maybe I should pause here. This is. No? For questions? No.
How do you see that the one with all pluses is vanishing is because of that prime H?
Well, that's really more to do with the fact that if you don't, it becomes unstable. I mean, the formula would not make sense with just one. If the curves that go through one twistor, they just stay there. They're constant. And then with zero twistors, they're not even there. So I guess you get the 3-point amplitude maybe if you had one twistor. If you, yeah. So it's not stable in that case. Okay. So then just to.
And by the way, there is one thing which always confuses me.
Yeah.
If I have a self-dual background, just a background, this means physically that in usual signature that if I send positive helicity and self-dual positive helicity gluons, they come out like self-dual, which is positive helicity with the outgoing momentum. So in amplitude, this is a plus plus minus minus, not a plus 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 plus.
Right. In working in
network again.
Okay, so in working in split signature, we're kind of sidestepping that kind of question. So first of all, we're working with wave functions on twistor space, and they are precisely sufficient data to provide the wave function on the whole of space-time. Sorry, I'm not sure what the best way to... yeah. Okay, I mean, it is. Maybe it's best to sort of think about that a bit more carefully later, because I'm not sure that I can answer it in a very coherent way. Okay, so that's one check. The high MHV degree, we get the Casazo-Skinner formula. When k equals 2, you can actually really drill down into the detail as to how this compares to something that you would actually want to compute on space-time. So how do we do that? So k equals 2, we've got two anti-self-dual particles. We can assume that they're momentum eigenstates, and you have some Möbius symmetry, so the integrals on the sphere are completely fixed, and you can reduce the integrals over the twistors as well. So we had delta functions in the definitions of these. They can actually get rid of 2 of the degrees of freedom. The Möbius transformations get rid of the integrals on the disk, and so we just get this formula here. We get the and at this point, you see, you're just looking at something that's going between 2 points on the twistor space. So it's, in some sense, we are just looking at a line through 2 points Z1, Z2, and so the mu coordinates of these Z1 and Z2 points can be thought of as just the space-time coordinates. You know, this is degree 1 now. It corresponds to a point in space-time. Mu1 and mu2 are the half each of the 4 coordinates on space-time. And we can see that this whole integral formula then just reduces to an integral formula over space-time of 2 plane waves for the anti-self-dual particles times this on-shell action. So now you can ask the question as to what is this on-shell action in real money on space-time? This just depends on the mu1, mu2, the data of the self-dual space-time. So what is it as a function on space-time now? And so let's call it omega of x. And omega of x has a very standard interpretation now. It's Plebanski's first fundamental form, or first potential for the metric. If you're a kind of pure mathematician, you'd know this as a scalar. So you'd think of mu1 as being complex coordinates and mu2 being their complex conjugates. And then this would be the expression for a Kähler metric. So this omega is the Kähler potential, or the Plebanski scalar for the self-dual metric, and that's what this on-shell action is. So you take this, you take the formula for this action, you start differentiating it and looking at the expansions of mu and so on, and you discover you get precisely the derivatives of omega.
Though there is usually a z bar for the Kähler potential.
That's right. So mu1 are the z's and mu2 are the z bars, or tildes. So okay. So that means that we can actually sort of write this down then, this MHV generating functional, as a formula just on space-time in terms of a Kähler scalar, or this Plebanski scalar of the space-time. And then this is meant to be, so according to the standard sort of tree-level formulae for amplitudes, this is meant to be the second variation of the Einstein-Hilbert action with respect to 2 anti-self-dual perturbations here. Just plain waves with momenta k1 and k2, and one can start off with the Plebanski gravity action. So this is the self-dual curvature wedge, the self-dual 2 forms, roughly speaking, and the self-dual 2 form is an expression like this. At least one of them is an expression like this with a wedge in there. And we can take the second variation of this. This is d gamma plus gamma wedge gamma for the metric wedge sigma plus. And then if the gammas are the 2 anti-self-dual fields, momenta k1 and k2, this part here can be thought of as the generating function for the MHV amplitude, and we can do a couple of integrations by parts here now to express it. The sigma is two derivatives of the omega. We can put them onto here, and we get this formula here.
Because d sigma plus is 0.
Yes, that's right. So on the self-dual background, actually this is a minus. Sorry, sorry. I've got stuff the wrong way round here. Yeah, it's our minus. These are the minuses as well. Yeah, self-dual implies that d sigma minus equals 0. So this first part kind of goes to 0, and then the second part, these gamma minuses correspond to the h tilde 1 and h tilde 2, and then if you integrate by parts on the these forms sigma minus, you end up with that formula there.
It's like the Einstein gamma action.
Yes, that's right. This is
Gamma minus.
yeah. So this is so it's Plebanski twice. That was a Plebanski's action. This is the Plebanski scalar, and we use Plebanski twice here to do this calculation. Two different versions of Plebanski. Okay, so here we drill down and we see then that this on-shell action, at least at MHV, is lying at the heart of the Einstein-Hilbert action, and at higher MHV degree that has to be the case too, because because that's how you think of these on-shell, these tree-level scattering amplitudes. They are the Einstein action evaluated on the tree-level field, but I don't have a direct proof of that. Okay, so that's the main part of the talk over. So just summary and conclusions then. So the takeaways then were that split signature self-dual vacuum metrics on S2 cross S2 corresponds to these generating functions of weight 2 on real projective tree space. And inside these spaces we have a scry S1 cross R that cut this S2 cross S2 into two different spacetimes. You could also try and reconstruct the spacetime from gravitational data on scry, but because it's not divided up into scry plus and scry minus, posing the shear on scry is too much because it generates its own future. It's anyway. So the Twistor data is a well-posed system in the way that expressing the shear is not. There's twice as much data as you want. So the Twistor space expresses this LW1 plus infinity symmetry directly in terms of its coordinate invariance, but also in the gravitons, or at least the way in which the gravity phase space is realized. And okay, so then the yeah.
If I do infinitesimally, you're saying if I deform H of U, I can generate physically different self-dual vacuum Einstein spaces.
Yes.
And are you saying, okay, and the Lie algebra is LW1 plus infinity?
That's right. So the real one is passive coordinate freedom multiplied by I. The imaginary one is generating non-trivial gravitons.
And in the usual affine Kac-Moody classification, this is an affine Kac-Moody, or it's another?
Oh, I doubt it. No, I don't know what it's Dynkin. I've never seen anybody write down a Dynkin diagram for it. Okay, so then the so the real generators then that are just they're passive coordinate transformations, but the claim is that the infinitesimal action of this LW1 plus infinity in the complex is given by the vertex operators of the gravitons. So that's how the action works in general. The MHV formula can be related to the Einstein-Hilbert action, and it can explain this tree formalism that V. Byrne and friends came up with in 1998. And everything, the whole thing is driven by this chiral open sigma model that computes gravity amplitudes. So it's a weird substructure to conventional gravity, albeit for most of you in the wrong signature. Okay, so I'm still not quite sure. I mean, so Thibault keeps pressing me on this. Can I actually see a Ward identity for these symmetries? I mean, I think you can, but it's not quite as clear-cut as it was in the ambi-twistor string case, because here we haven't got a kind of full correlation function for the formula, so it's not really coming out of a... So the Ward identity more at the level of the sigma model, but it's not a complete sigma model. Some extra terms are inserted by hand. We noticed we had a det prime H and a det prime H tilde. One of them is corresponding to this LW1 plus infinity on Twistor space, and the other one on the dual Twistor space. This is the sort of self-dual part, and that's the anti-self-dual part. So at MHV, everything is essentially in the H, but they're both needed beyond MHV, and these symmetries don't really commute in an obvious way. There's an ambi-twistor string, which I didn't tell you about, which allows them both to coexist, and that you have vertex operators depending on both H and the H tildes. So the vertex operators obey this Poisson bracket relation for the LW1 plus infinity, as you'd expect, as part of their OPE, but the OPE between the self-dual and the anti-self-dual parts is a mess. But the actual formulae you get are not bad, and you get these so-called scattering equations, which are the kind of the residue equations that you get for the final amplitude formulae. So it's still slightly unclear as to how you can see both sets of symmetry operating at once. And I'll just say that there is something reasonable you can say about the one loop or plus amplitude in this context, so you can write down formally for that. So there is an extension to one loop at that level. Although it's not the full one loop amplitude, it's not the dialogue part, it's the rational part.
This is, everything is in D equal 4.
Yes.
And you are going, the next slide is about the supergravity aspect.
No.
No.
Another time, it's essentially tea time. I really do have to stop here. So thank you.
Thank you.
Okay. No, supergravity, well, I mean, the supergravity does exist in this formalism, but...
But D equal 4, simple supergravity, or N equal N, this thing?
Well, okay, the N equals 8, Dave Skinner has a nice N equals 8 twistor string that gives rise to a very closely related... I mean, the Casazo-Skinner formula was an N equals 8 formula when it was first written down. So many ingredients exist for N equals 8, but I haven't understood the details for this sigma model.
No.
Oh, sorry, there's...
Just a question. Can you again explain what do you mean by small condition when you produce the one-to-one correspondence between twistor functions and self-dual structures on S2 times S2? You said small. What?
The word small is just meant in the context of implicit function theorems. So there's some use of an implicit function theorem around the flat case, and they always say the implicit function theorem works in some small open set in a Banach space, which you very rarely choose to define precisely.
So it means the slope usually is smaller than 1, no?
Because
the implicit
no, I see the origin of it.
Yeah. So and that applies sort of to everything, to the holomorphic disks and also to the I can't remember if it also applied to the rigidity of the complex structure on CP3, or maybe now CP3 is rigid. Yeah. So there are various steps at which some smallness was used.
So CP3, like Romanov said, might not be rigid after all, because experts say it is rigid.
That's right. I'm not sure. Certainly at the time of writing, I don't think it was proved. It may have been proved since. CP2 is unique. There is one. So when we were doing the Zoll surfaces story, we needed CP2, and we could just say, CP2 is unique. There is only one complex structure on CP2. But CP3, my memory is that we weren't allowed to regard that as a done deal.
H1 is 0, right, of the tangents?
Oh yeah. So it's rigid. But you need to be a hardcore algebraic geometer to know that it's that there is no other it's actually been rigorously proved that there is no other complex structure on CP3.
Okay, thank you again.
Thank you.